Hello, young physicists. Ever wonder why waves don't just travel in straight lines like arrows but sometimes bend around obstacles? Well, that magical phenomenon is called diffraction. Think of it as waves sneaking around corners, but only when the gap or obstacle is roughly the same size as their wavelength. Imagine you're at a concert and the sound waves bend around the pillars to reach you. That's diffraction in action. Now, this bending leads to an interesting dance of waves called interference. According to Huygens' principle, every point on a wavefront acts like a tiny new source of waves, creating secondary wavelets that overlap and combine. When these wavelets meet, their peaks and troughs either add up or cancel out, leading to bright and dark patterns. The distribution of light intensity we see in diffraction depends on differences in the path lengths and the phases of these wavelets, causing certain directions to be bright and others dark. This results in a pattern of minima, where light is dimmest, and secondary maxima, where it brightens again, which is quite different from the sharp shadows geometric optics predicts. So, diffraction beautifully reminds us that light and waves aren't always neat and tidy. They like to play with bending and blending. Alright, now when can we actually see diffraction happening? The key factor is the size of the aperture or obstacle compared to the wavelength of the wave passing through. Significant diffraction occurs when the slit width, let's call it A, is roughly the same size as the wavelength lambda. For light waves, which have wavelengths on the order of 10 to the minus 7 meters, we need incredibly narrow slits, almost microscopic, to notice diffraction patterns. That's why you don't see light bending noticeably around everyday objects. But with radio waves, whose wavelengths range in meters, everyday items like buildings and hills become pretty good dancers of radio waves, causing significant diffraction. That's why your radio signal can bend around obstacles. The spread of the wave after passing through the slit is often measured by an angle theta, which approximately equals the wavelength divided by the slit width. So, smaller slits or longer wavelengths mean wider spreading. This is why closing one eye slightly gives you a blurry, more spread out image, a little everyday diffraction. Let's zoom in on the classic single-slit diffraction pattern and talk about its brightest feature, the central maximum. This bright fringe right in the middle is the showstopper and is about twice as wide as any of the smaller side lobes or secondary maxima on either side. Mathematically, the first dark lines or minima on either side of this central bright fringe occur where the slit width A times sine theta equals plus or minus the wavelength lambda. In other words, a times sine theta equals plus or minus lambda. This is the condition for the first minima, where destructive interference knocks out the light. For small angels, the angular width of this central bright fringe is approximately twice lambda over A. That means the broader the slit, the narrower this central maximum becomes, and vice versa. Most of the diffracted energy funnels right into this central bright spot, making it the brightest and most intense part of the pattern. So, even though wavelets spread out and interfere everywhere, the main action stays front and center. Sampling deeper into the single-slit pattern, we find a series of dark and bright fringes beyond the central maximum. The dark fringes or minima form where the slit width A times sine theta equals m times lambda, with m being plus or minus 1, 2, and so on. Simply put, these are the angles where the waves inside the slit cancel each other perfectly. The positions of these dark bands on the screen, located at distance d from the slit, can be calculated as y sub m equals m times lambda times d divided by a. This formula tells you exactly where on your screen the minima will appear. Between these minima lie the bright fringes or maxima, but unlike the central peak, they are fainter, uneven in intensity, and spaced unevenly. These maxima don't have sharp peaks like the classic interference pattern from two slits. They fade quickly as you move away from the center. So, this pattern is a little like a fading wave concert. The main performer is brightest, with the loudness and excitement dropping off to the sides. Now, let's get mathematical. The total amplitude of the wave coming through a slit is found by adding up all these tiny wave contributions, or phasors, from each point along the slit. Because each point differs slightly in phase, there's a phase difference delta, equal to 2 pi times a times sine theta divided by lambda. The intensity at any angle theta is proportional to the square of the sine of beta over beta, where beta equals pi times a times sine theta divided by lambda. Formally, this is intensity I of theta equals I0 times sine beta over beta squared. I0 is the intensity right at the center when theta is 0. If you imagine plotting this intensity against theta, you'd see the central peak standing tall at 0 degrees with smaller side fringes on both sides that diminish in brightness as they get further away. This graph shows the broader central maximum and the series of fading maxima and minima, contrasting sharply with the equally spaced, equally bright fringes in double-slit interference. So, this beautiful sinc-squared pattern is the fingerprint of single-slit diffraction. Let's put our understanding right into practice with a quick example. Suppose we have a slit width of 0.25 mm and light of wavelength 600 nanometers shining through it. We want to find the angle θ1 where the first minimum in the diffraction pattern appears. Using our formula for minima, a sine θ1 equals lambda. Rearranging, sine θ1 equals lambda divided by a, substituting the numbers, lambda is 600 times 10 to the minus 9 meters and a 0.25 times 10 to the minus 3 meters. Doing the math, sine θ1 equals approximately 2.4 times 10 to the minus 3. Taking the inverse sine of this value, θ1 is about 0.137 degrees, a very small angle, which justifies using small angle approximations in our calculations. This tiny angle shows how precise and subtle these diffraction effects are, although visible to experiments and devices sensitive enough to detect them. Now, you might wonder, what's the real difference between diffraction and interference? Both produce patterns of bright and dark fringes, but they have key differences. Interference involves two or more coherent sources of waves, like the slits emitting waves with a fixed phase relation, creating distinct, evenly spaced bright and dark fringes caused by differences in path length. Diffraction, on the other hand, arises from a single wavefront that passes through a finite-width slit. The wavefront internally interferes with itself, producing a pattern where fringe widths vary and intensities fall off rapidly. Mathematically, the intensity in interference varies as the square of the cosine of phi, where phi relates to the phase difference between waves, while in diffraction, intensity follows the sine beta over beta squared rule we discussed earlier. So, interference is like a perfectly choreographed duet, whereas diffraction is a soloist improvising within a limited stage. Both fascinating, but with their own unique rhythm. To wrap up, remember these key points. The condition for minima in a single slit diffraction pattern is slit width times sine theta equals m times lambda, where m is an integer. The intensity distribution follows the formula I of theta equals I0 times sine beta over beta squared, with beta being pi times slit width times sine theta divided by wavelength. The angular width of the central maximum is approximately 2 times lambda over a. Diffraction effects become most noticeable when the size of the aperture is on the order of the wavelength. In essence, diffraction teaches us how waves bend and interfere within a single wavefront, creating beautiful patterns of bright and dark fringes that fade rapidly beyond the center. Mathematically, we use phasor summation to understand these patterns. And that, my friends, is the wave optics magic behind diffraction. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.